Welcome back, everyone. So today we got another example that shows you how to use or how to solve for variables in your closed system energy balance. So we're going to be doing change in elevation, change in velocity, change in internal energy, heat transfer, and the work performed by the system. And at the end of it, the formula for a closed system energy balance is delta PE plus delta KE plus delta U equals Q plus W. That is potential energy, kinetic energy, internal energy, plus your heat and your work. Okay, so let's get to it and see what we got. Alrighty, so let's jump into part one. So part one is a change in elevation, right? And we said we have a change in elevation from 50 feet to 1,000 feet. Now in physics, you learn that based on the changes in elevation or certain reference points, your potential energy is going to increase or decrease, and it's a matter of how you define your point of reference. In this case, we're going to assume our point of reference is sea level. Now we're saying that we're initially 50 feet above sea level, right? So that's where we're at now. But then we're going to go up another 950 feet higher into the air. Therefore, we're going, our potential energy is increasing by another 950 feet. So mathematically, this is what it looks like. We said the mass is 10 kilograms, right? So our potential energy is going to look something like this. Since we're going up another 950 feet, that is the difference in elevation, we can multiply the 950 feet by 1 meter, which is going to be divided by 3.2808 feet. Okay, so what we're doing here is we're just converting feet to meters, and it's going to make it easier for us to play around with in a bit. So, oops, a little sloppy there, but that's just a unit conversion factor. If you were to Google that, you would see that one meter equals 3.2808 feet. And then we're going to multiply this by the gravitational constant of Earth, which is going to be 9.81 meters per second squared. And then we're going to multiply this. Let me write this down. By 10 kilograms. And that's the mass of our system as specified in the problem. And at the end of it, we're going to get 406.2 joules. Okay? And that change in potential energy is equivalent to this joule constant, 28,000. That's how you would calculate the potential energy for that system when you change the elevation. Now here's another cool tip to keep in mind. This could also be rewritten as so. Instead of joules, there's a unit conversion factor where 1 joule equals 1 kilogram times meter squared over seconds squared. So you could also rewrite this as kilograms times meters squared over seconds squared. Okay? And that's totally valid. You may write it one way or the other depending on what you're trying to solve in the problem. So this is part one, and you have just found your answer. That's how you find potential energy. Feet to meters, SI unit, multiply it by your gravity constant, and then the mass of the system, which is given. Okay? So let's look at number two. Number two is a velocity change from 10 meters to 100 meters per second. So the velocity is changing from 10 meters per second to 100 meters per second. Okay? So what you're calculating here initially first is your change in velocity. What is that? Oh, great. Just subtract 100 minus 10 and you get 90 meters per second. But what do you do with that? Well, with this, you could plug it into your kinetic energy formula. And if you remember from physics, kinetic energy formula is 1/2 mv squared. Okay? And in this stoichiometry series, we write that as 1/2 m dot or mu squared, depending on whether your mass is flowing through time. But here it's not, because it's a closed system, so no mass is going in, no mass is leaving out. That's why we do not put a dot up here, okay? No dot goes there because it's a closed system. So we plug stuff into this formula, and we know that the mass is 10 kilograms, and the velocity is 90 meters per second, and that's squared, right? Because u is squared. Plug that into your calculator and you get 40,500 joules, or 40,500 kilograms meters squared over seconds squared. That's totally valid as well. And that's how you calculate the change in energy based on your velocity. So number 3, we said we had a change, or have a change in internal energy. Okay, so how do we approach that? We're told that the change in internal energy is from 10 kilojoules per kilogram to 2,000 kilojoules per kilogram. And of course, the difference of that is 1,000 kilojoules per kilogram. You're taking your final minus the initial, you get a positive number, 1,000 kilojoules per kilogram. Okay. So then what you do is you write this down here, kilogram. What do you see about this that makes it easy for you to calculate your energy component? Notice there's a kilogram here, and notice that you're told that your mass of the system is 10 kilograms. Therefore, you could write 10 kilograms up here, as so, and then cross this out, and then plug this into your calculator, and you're going to get 10,000 kilojoules. Okay, but I want this to be in joules, so kilojoules at the bottom, joules at the top, 10 to the third. Great. And now we have 10 million joules. Okay, that's change in internal energy, the mass of the system times the change in internal. So number 4, we said we have a heat transfer to the system. That heat transfer is 10 to the 4th kcals. Okay, so 10 to the 4th kcal, let's convert that to calories, just calories, not kcals. As a reminder, whenever you're given a k value, or a kilo, mega, deci, centi, whatever, you want to convert it to the base unit. It's going to make it easier to calculate or mess with throughout the problem. And that's with most problems in stoichiometry. So then we know that 1 kcal is equivalent to 10 to the 3rd cal. Okay? And then what we're going to do here is, if we look at our unit conversion factor table, and that can be retrieved anywhere from Google or your textbook, you're going to see that 1 joule is equivalent to 0.23901 cal. Okay? And then you plug that into your calculator, and you're going to get 4.18393 e to the 7th power. Okay? And that's going to be in joules, of course. And then finally, number 5, we have, we're told that there's going to be work performed, and that work performed is 50 kilowatts per hour for work performed. Okay, so let's write this down here. And what do we multiply this by to get the final value we want, which is joules? If we look at our unit conversion factor, we find another one that says 1 joule is also equivalent to 2.778 times 10 to the negative 7th power, and that's kilowatts per hour. And we plug that into our calculator, and we get 1.79986 e to the 8th power, and that's in joules. Don't forget your units. Now, we solved a whole bunch of things for this problem, right? Let me ask you something else. Would this satisfy our energy balance equation for a closed system based on the values we just found? What's our formula? Our formula is potential energy, change in potential energy, plus the change in kinetic energy, plus the change in internal energy, and that should be equivalent to the heat plus the work of the system. So if we start plugging in our values, and plugging in we will, we have 28,406.2 joules. We have kinetic energy, which is 4,500 joules. And we have change in internal energy, and that's 10 million joules. Notice we could add them because they all have the same units. That's the great part. We all have the same units. We could add them. Now, they're supposed to be equivalent to heat and plus work. So 4.183 e to the 7th. I'm going to cut out some of the sig figs here. And then we're going to add that to, let me make this a little smaller so it's easier to see. Plus negative 1.7998 e to the 8th power. Okay? And after summing these values up, you're going to find that this does not equal that. And therefore, we say that our values do not satisfy the closed energy balance equation. And as a result, this system is not valid. There's something else going on, or there's something we haven't taken into account, and that's why our values aren't equal. They should be equal in any real world scenario, assuming you take into account accumulation, output. But you know, those are things or topics for another video. If you have any questions or concerns, feel free to leave them in the comment section below, and I'll catch you in the next one. Take care.